Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Eileen Gonzales with us today. Hi, Eileen.
Hi. Good
How
to
are
see
you?
you. Good.
Where are you at? What's your geolocation?
I have just moved to Ithaca, New York. I am starting my postdoc as a 51 Pegasi B fellow.
Awesome. Has fall started yet in Ithaca?
It feels like it's starting to start. It's starting to get a little cold, chilly at night, so.
Okay, very good. Winter, fall coming, very good. That is an awesome picture there of planets off to your left, I think, if I've got the parity right there.
Back over here?
Uh-huh.
Yeah, so this is the PSO 318 poster from the NASA Exoplanet series.
Very cool, very cool. So are classes actually happening at Cornell, or are students going to classes, or is it all online, or what's the deal at Cornell?
So they're hybrid method. So I think classes over 50 are all online, and then some are in person, but most are online.
Okay, very good. Very cool. So what do you like to do for research, Eileen?
So my research actually focuses on understanding the atmospheres of brown dwarfs and low mass stars. Particularly, I have been working on doing atmospheric retrievals of brown dwarfs lately, particularly old ones known as subdwarfs.
Mm-hmm. Very cool. And that will lead us into this really lovely article, excuse me, on a reanalysis of the fundamental parameters and age of Trappist-1. Eileen, take us away.
Okay. So this paper actually was kind of a side project in my thesis. Most of my thesis work was on subdwarfs, but Trappist-1 was something that we were super interested in because of its contradicting age indicators. Okay. So previously, from a work from Bergasser and Mamachek in 2017, they went through a slew of age indicators, and a majority of them, kind of driven by the kinematics, put it towards an older age while using something called the Ehlers and Lou gravity sensitive indices that put it as being a young object. And they kind of threw out that young indication saying, oh, it's probably something that's triggering the indices we see with M dwarfs for low metallicity objects. Those can show up with this intermediate gravity, and those for sure aren't young. So it's got to be something like that. So let's throw it out. So we thought that was really interesting and said, well, let's do a more detailed approach and look at the SED of Trappist and try to dig out what we can learn about its age.
So when you mention young and old ages, so sort of what are we talking here for ages and years, or?
So like young is less than 500 million years, and old is, you know, from like 500 to age of the universe kind of thing.
Okay, very good. Thanks.
Yeah. Okay. So first off, Trappist-1 is a very popular object. As you may or may not know, it has 7 rocky Earth-sized planets with 4 of them in the habitable zone. So it's a real interesting object to look at if we want to understand the habitability of small Earth-sized planets around late type M dwarfs. So if we scroll down to, I guess I could probably talk about the discovery of Trappist-1. Okay. So right in this section, first off, Trappist was found a long time ago. In the 2000s, it was kind of just a regular old M dwarf, a part of a survey trying to fill out the population of nearby M dwarfs, and there was really nothing special about it. So there's a couple of things on the star itself. It's actually got a lot of spectra and photometry, but it wasn't until 2015 with the Trappist telescope when it was found to have 4 planets around it. We didn't actually know until follow-up data that it actually had 7, and the transit from one of them actually contained the transit information of a few other planets. So moving down to figure 1, I am showing what the spectral energy distribution, or the SED of Trappist, looks like. Mm-hmm. So here I'm just compiling all of the photometry that we have for the object. And 2 of the spectra, we're using the medium resolution fire data. and optical from the RC spectra. So this is composed using Joe Filipazzo's SED kit. So I take the spectra in photometry, and because I'm using the parallax from the Gaia Space Telescope, I can get out an empirical bolometric luminosity.
Cool.
And I combine this bolometric luminosity with evolutionary models, and we can estimate a radius based on a rough age. And we didn't really have a set age range for Trappist. So we assumed either a field age for brown dwarfs, which is typically half a gig a year to 10 gig a years. And then later on, we make an assumption of saying, okay, if this is young, if we assume it has an age of less than half a gig a year, what fundamental parameters come out? So we can get the fundamental parameters from this method. And what I do in this paper is I try to compare Trappist to objects of similar temperatures to see how does its SED compare to other objects of either when you assume a field age, how does their overall shape look, and how does the near infrared band by band regions look? And then if you assume it's young, doing the same thing.
Right.
So if we scroll down to, I believe, the next figure, figure 2.
Let's go to figure 2. Ooh, lots of comparative tables.
Yes, of all of the many, many comparative samples.
Great. It's awesome. Great data set. Okay, there we go.
So figure 2 is showing 4 of the samples. So the first one, 2A, is Trappist compared to field age objects. B is Trappist compared to young objects of the same temperature. This is all assuming Trappist is field age.
Okay.
Then figure C is comparing it to low metallicity objects. And figure D is now we're comparing objects that have the same bolometric luminosity as Trappist.
Okay.
So from looking at these 4 figures overall, just by eye, we see that Trappist really fits a field age M dwarf. But you can see there's a couple of regions of overlap in the optical with the low gravity objects. And there's kind of a couple interesting regions of overlap with one of the objects of the same bolometric luminosity. So
when you say on this one on C, when you said low metallicity, what is that roughly? What is that metallicity? Fe over H or something?
Yeah, it's Fe over H. And these are, they're not like super low metallicity. It's probably around like a -1 to -2 sort of objects we're looking at.
Okay. Thanks.
So yeah, so from our overall, we see it looks most like a field object, but then we wanted to look at those near infrared band by bands because it gets that intermediate gravity signature. We want to see, okay, what spectral features are kind of pulling out that, and do we see that it looks more like a low gravity object, or is there maybe sort of a blend of these features and trying to figure out what it could be? So the next figure is showing, I believe it's figure 3, has the comparatives in, well, figure 3 is zooming in on one of the particular regions in the SED where we were trying to see, is there some sort of temperature structure that's standing out on how they're stacking on top of one another. But the more interesting thing is figure, I believe it's probably figure 4 then.
Okay. Slide figure 4. Ooh. Okay, let's decrease that to get them all in there.
Yeah. So this is showing the near infrared Y, J, H, and K bands going across from A through D to look at the individual features to see what does Trappist match to and where is it differing. So Trappist is in black in all of these figures.
Okay.
And what's really interesting is while it tends to match field age objects in the overall, we definitely see it fitting some of these low gravity objects. So in figure A, you can see like a really good match to this low gravity M9, 0436.
Mm-hmm.
And in previous works, the spectra was kind of matched to VB10. So that's doing a pretty good fit as well. So those aren't differing a huge amount by eye.
Yep.
Kind of the big difference is looking at the sodium and potassium doublets, which is in panel B. So this is in the J band. we see that Trappist has very deep potassium doublets. So that's at around 1.17 and 1.25. And you expect that for something that has a higher surface gravity, while for the low gravity objects, you see that they have much shallower absorptions. Another big thing that stands out for low gravity objects is the shape of the H-band. So in figure C, the orange object, 0608, you can see it's really peaky and triangular. So that's what you expect for a low gravity object, but we don't really see that for Trappist. We see it being a little bit peaky, but nothing super extreme, driven it away from the field objects. And then again, you know, we can look at features, particularly in the K-band, that sodium absorption line. You see that for field H, but you don't see that for the low gravity. So looking at the band by band, you're really seeing that there's kind of this blend of some features that stand out that look low gravity, while we have others that look field age. So it's still kind of leaving us puzzled of, okay, then really what's the age of Trappist?
Right.
So again, we do this with the objects of similar bolometric luminosity.
Okay.
And we're kind of coming out with the same conclusion. So the next step in this paper, I believe when we hit figure, not 5, maybe figure 6.
Figure 6, distance calibrator SEDs.
Yes, so figure 6 is now saying, okay, if this is us assuming the conclusions we drew from the last section was, let's assume Trappist is field age. Okay. So now we're saying, okay, well, if Trappist is actually young object, what we've done for the comparison isn't going to be valid. So let's use the age constraint of it being younger, which is going to give us a slightly larger radius and a cooler temperature. And now let's come up with the exact same set, but at a lower temperature, and see, okay, what does Trappist match? Yeah. And really from this, you see that Trappist doesn't fit with the field gravity objects because it's going to be hotter. The low gravity objects, again, we're seeing a little bit of that overlap, and you also see a little bit of that with the low metallicity. But from doing the band by band comparisons on this, it really points towards Trappist looking more like it being a field age and not being a young object.
Okay.
And then interestingly, in Burgasser and Mamachek's paper, they compared Trappist to a couple of objects in the SPLAT database. These came from just taking the near-infrared spectrum of Trappist and running it through and saying, which object does it look most like? So we go ahead and make the SED of those objects. Okay. That is either figure 7 or 8.
Let's go. Figure.
Yeah. So 7's the band by bands. So I think figure 8 is the overall SED.
There we go.
No, figure 8 is not. We can come back to figure 8.
We can. That's the sodium ones.
Yeah.
Calibrated SED. There you go.
Yeah. So figure 8 is looking at the 3 closest looking objects in the Burgasser and Mamachek paper.
Okay.
And just from looking at the SED, you can see 2 of them are definitely too hot compared to Trappist. So one's a field age object and one's another one of these intermediate gravity ones. But we see that LHS 132 does a really good job of matching on top of Trappist. So this is an object that we want to look at further on in our study. Okay. So if we go back to figure 8, because we saw some of that overlap with the low metallicity objects, here we're looking at the near infrared sodium doublet in panel A, and then again those potassium doublets in panel B. So the really interesting thing of panel B, in my previous work on looking at subdwarfs and making their SEDs, we noticed a trend where the 1.17 doublet is deep, and we expect to see that for a low metallicity, high gravity object, while the 1.25 doublet is very shallow. And that's not what you would expect, because these things are high gravity, we expect to see deep lines. And this is kind of a trend that we see with subdwarfs. We wanted to see, oh, is this particular feature shared with Trappist-1 in these subdwarfs? And we're seeing that Trappist-1, it's not having shallower lines. It's looking more like what we'd expect for a field age source. So we could really kind of throw out that possibility that maybe it has low metallicity that could be tricking the indices to giving that intermediate gravity.
Yeah, okay.
Yeah. So after we did these band by band and overall SEE comparisons, we wanted to place Trappist in context with the low gravity population of brown dwarfs and low mass stars. So down in figure, let's see, figure 10 and 11, we are running through the Ehlers and Lou indices, but on a couple of spectra we have for Trappist.
Okay.
So the 3 different black symbols correspond to the SPECS prism data, the SPECS SXD, and then the FIRE medium resolution. And what we expect to see is if it is coming up with a field gravity indicator from the Ehlers and Lou system. So you can either have field gravity, intermediate gravity, or very low gravity. The field should land on the blue strip. Between the blue and the dotted line is where the intermediate gravity objects land. And then below that is where very low gravity.
Got it.
So running their indices on our various spectra, we're also getting that it's coming out as intermediate.
Yep.
They also have particular equivalent widths, and we want to compare that to the objects that have equivalent width values. A lot of them are coming from Emily Martin's 2017 paper, so that is figure 11, and seeing where it lands. And It's again kind of close to field, but also pretty close to that thin strip of where intermediate gravity is. So the next thing we did was let's place Trappist in context with its fundamental parameters to field low gravity and low metallicity objects. So if you go to figure 12, we have Trappist kind of placed where it is for its bolometric luminosity, and figure 13 is its temperature. So there's so for figure 12, we have the field age objects in gray, and they kind of make a nice strip. And with the low gravity objects, they kind of peel off in those earlier M's.
Okay.
So there's 2 trends, and right where Trappist is right where those 2 trends for low gravity versus field objects directly overlap. So there's really no easy way by putting it on a spectral type versus bolometric luminosity, or temperature versus spectral type, that you can pull out and say Trappist belongs with one of these. It's still kind of blended there.
Yeah.
So we wanted to look at kinematics of the low gravity population to see how can we place Trappist in context with those.
Yep.
So further down, and this is doing the same thing with 2 mass and Ys. So again, it's kind of blended. There's nothing we can tell. But I think figure 16, yeah. So this takes the UVW velocities of low gravity objects. So we have the 2 kinds, the very low gravity or the gammas, and then the intermediate gravity or the betas. And we place ones that are in known nearby young moving groups and one that's are the difference between the solid and the open circles. So we see for the very low gravity objects, it doesn't matter if they're in or not in a nearby young moving group. In UVW space, they're landing in the same area. But for these intermediate gravity objects, some of them land with the very low gravity and others land further out. The dashed lines are kind of indicating the separation between the thin disk and the thick disk.
Okay.
So we're thinking that this is, in fact, the intermediate gravity objects are not a single population, but 2 populations. So objects that are actually young, and then objects that appear to be young for some other reason.
Yeah.
So interestingly, in the same region as Trappist is Teegarden star, which is also known to have a planet. And our thought was maybe there's some sort of interaction between the planet and the star that could be driving this intermediate gravity. And then LH132 that match Trappist really well is in this region. So these objects could be great targets to go after for looking for planets around low mass stars. Like this could be an interesting signature of what could be the population to go look for.
Nice.
So our next figure, figure 17, kind of also solidifies this when you're looking at the tangential velocities.
Okay.
Yep. So we have the distribution of tangential velocities for very low gravity objects in groups and not in groups. So that's figure A, where we see that the distribution, the peak of the distribution is about the same at around 20 to 25 kilometers per second. But then for those intermediate gravity objects, we have the peak being in about the same place for ones that are in groups. But for ones not in nearby unmoving groups, we see this larger tail. And while we're dealing with small number statistics, TRAPPIST-1 ends up being in that fat tail. So this could be pointing towards maybe these are some interesting objects to look at and see, do these possibly have planets around them? Our thought for the interaction is it could be tidal interactions from planets. But after discussing about some follow-up work, it's thought that that is probably too weak. The other thing is TRAPPIST's radius could be inflated due to its magnetic activity, but we're not sure what the cause of the inflation is from the magnetic activity.
Fair enough.
Yeah.
Interesting.
Yeah.
Very cool. So, thank you for sharing it.
Yeah.
And let me ask then, where do we go from here, or where do you go from here? Where does the community go from here? There's things of interest looking for this population of TRAPPIST-1-like objects? Is there new telescope capabilities coming online? This kind of stuff.
Yeah. So where to go from here? There's so many interesting things to look about TRAPPIST. It's still such an interesting system to try to understand. And I think what I am most interested in that came out of this paper is really understanding these intermediate gravity class objects. Intermediate gravity doesn't really tie to youth, and we're really not sure what intermediate gravity means. And I think looking at this population of objects that appear to behave like TRAPPIST, if we have the kinematics, maybe these things aren't young, really digging into what is causing that intermediate gravity signature, and is it interactions with planets or is this something else, I think is the most interesting thing to go after. And me and a couple of collaborators were on a proposal to try to go after some of these targets and try to figure this out.
Okay, because you mentioned in the beginning that this was just sort of an offshoot from your main work, so it seems like it's opening up a little bit into a whole line of research.
Yeah. The kind of bulk of my thesis work has been doing atmospheric retrievals. So something I'm really interested is running an atmospheric retrieval on TRAPPIST. I'm not sure how exciting it will be since this object is a little bit hotter, so I'm not going to see lots of cloud signatures. I've been looking at cooler objects, but I still think it would be really interesting to do an atmospheric retrieval on TRAPPIST-1 and see what else that can bring us.
Yeah. Is there new telescope capabilities coming online? Like, can Plato do something with this object or something like that? JWST? I'm just curious.
There definitely is with JWST, particularly with my work on atmospheric retrievals. Really having the capability to get mid-infrared data has been very useful in understanding cloud features of objects, and having more data is also very helpful for constraining SEDs and really getting to tighter fundamental parameters of these sources.
Cool. Eileen, Thank you very much.
Thanks.
And for those of you who are interested, you can go ahead and reach out to Eileen and talk about Trappist 1 and brown dwarfs and other stuff. And everyone, thank you so much, and we will see you on the next one. Bye-bye.
Yes.